Welcome back to the lectures on partial differential equations. In the first two lectures, that is last 1 hour lecture, 2 half an hour lecture, we have given a brief about the whole program and we also introduced some notations, some remarks in the last couple of lectures. Now, in the next 2 hours, essentially 4 lectures, we will present some preliminaries required for this course. As I mentioned or introduced already, giving preliminaries in detail is not possible because the theory of partial differential equations, you need to know plenty of preliminaries which you have studied, and I advise or suggest you go through it. So, in the couple of hours I will describe 2 aspects. There are many things like multivariable calculus, like inverse implicit function theorems, you should know about it. Another important aspect is the surface measure, surface integration and all that. All that requires some amount of study, some amount of, if you are not familiar, you have to spend some amount of time there. Then there are something about ordinary differential equation, Fourier transform, some good functional analysis and all that. As I said, it is not possible to cover all the preliminaries. So, in the first I mainly restricted to 2 preliminary things. One is about the multivariable calculus, that I will do it in 1 hour. I will just want to state inverse function theorem and implicit function theorem only stating, but then I want to develop the reasons and ideas. So, main motivation is to introduce to you to the ideas behind implicit function theorem and inverse function theorem, those who are listening for the first time. But in the second 1 hour 2 lectures, we will introduce to you an intuitive ideas behind the surface measure and try to tell you about Green's theorem and divergence theorem, which we will be using it frequently throughout this course and also in the next course which we are proposing. So, let us do what we call it so we call what is preliminaries. Okay. So, in the preliminaries, let me do some multivariable calculus. Okay. This is about the solvability, this show, and some of the preliminaries, if necessary, we will introduce to you as and when required. So, this is about solvability. Okay. You want to solve equations of the form f x equal to y or equations of the form in the implicit form, this is in the explicit form, and f can be a mapping here. In this case, f can be a mapping from Rn to Rn, and here f can be a mapping from some Rn cross Rm, y will be an M to Rn. So, you can have this kind of mappings. So, though I will be restricting myself to this kind of equations, let me also tell you the theory which you are developing actually can be used for more general cases, which I will not do it, but I advise you to learn. So, you can have from x to y, and x and y can be normed linear spaces. Why this kind of abstraction, and it can be infinite dimension and all that, you can convert your PDE and other problems to this abstract problem, abstract solvability, and these theorems can be very handy when you want to solve it. So, let me restrict myself to the case here. So, let us do start with some examples. Okay. The simplest example you can think of it. My f x is f from R to R, f x equal to x square, where f is from R to R. So, you want to solve x square equal to y. So, let us look at a figure here, and this is your x, this is your y. So, start with. So, let us look up at a, so let us draw, this is familiar to you. So, let me draw my parabola. So, this is your parabola, so you see, and then when you try to solve this, so you want to solve this one, this equation is very familiar to you. So, you know that 3 cases y less than 0, no solution, y equal to 0, only one solution, and y greater than 0, 2 solutions, right. So, there is some trouble at the origin, that is what you see, trouble at the neighborhood of the origin, that is what you immediately see it. So, let us do what is happening here. So, this is the case. So, if you have this one, so if you look at here, for given y you have 2 solutions, 2 solutions are obtained. So, for this y 1 you get this y here, you have 2 solutions x 1 and x 2, you have that 2 solutions there. On the other hand, when you choose y equal to 0, no thing, and y if you choose here, no solutions. This is something like you are looking for a global solvability, but then there is a concept of local solvability. What is local solvability? Tell you what is this local solvability? I am looking for a point x naught here. So, let me choose another color. So, look at here x naught, and let me call it y naught is equal to f of x naught. So, that is by x naught, you choose x naught positive and let y naught be f of x naught. Then look at here this point, this is your y naught, you can choose a neighborhood here, and that neighborhood you can come up to the origin, and but this point can go to up to infinity, the neighborhood, and this neighborhood if you look at it is inverse. For every y here you can have a, so you get a neighborhood here, so you get a so you have a neighborhood here, you have a neighborhood here, and for every y in this neighborhood, for this neighborhood you have a unique x satisfying this, you see. So, that means in fact this neighborhood can up to 0 to infinity. That means if you restrict your function f 0 to infinity to 0 to infinity, then unique solvability, that is what you see that way. That means you have a neighborhood of given an x naught, there is a neighborhood of x naught and there is a neighborhood of y naught, between that you have a 1-1 bijective mapping. Unique solvability means, so the unique solvability is you are looking for the bijectiveness of that map. So, you have thing. So, what is the trouble here? So, let me go to okay. So, you understood the local solvability for a neighborhood, you have a neighborhood there, there is a neighborhood of x naught and there is a neighborhood of y naught. On that you have the unique solvability and you can put your inverse maps there. Okay. This is the same case. So, now let us look at the another example. Another example, I take f of x y is equal to x square plus y square minus 1 equal to 0. You know that this is the circle. I am just trying to motivate you. Yeah, in the previous example, you immediately see that f of x, if you look at the differentiation, this is nothing but 2x. So, f x at 0 is equal to 0. So, probably this could be the possible trouble. I will come back to this one. So, before coming to that example, let me give you one more motivation. We will come back to this example. Let me have one more motivation. The kind of example familiar with that. Suppose f is a mapping from R to R. You already seen this example. So, I am recalling and trying to connect with that and choose a point A in R. If I choose a point in R such that f prime of A not equal to 0 and assume f is a C1 map. F is a C1 map means it is a continuously differentiable function for which, that means f is differentiable and its derivative f is also continuous, it exists. Then since f prime is continuous, by continuity there exists a neighborhood u of A. You can have a neighborhood and that can be an interval. So, let me write it in the interval form. Okay. So, let me write it in the interval form. Okay. There exists a neighborhood, in fact it is an interval I, there exists an interval I containing A, in which on that neighborhood your f prime of x is not equal to 0 for all x in I, right. That means there is a neighborhood of A for which f prime is not equal to 0. That means this implies f prime of x is greater than 0 for all x in I, or f prime of x is less than 0 for all x in I. That immediately, so if assuming that f prime of x, if f prime, so that means immediately tells you, that means implies f is monotonic, that is the meaning. Either f prime is increasing or f prime is decreasing, and when in that case f is increasing, you can take f from I to f of I. Since I am taking f of I, its image, it is known to immediately and it is monotone, that means that it is also 1 1 and I is an interval, f of I is also an interval, this is also an interval. Okay. That immediately tells you this is 1 1 on 2. Okay, so it does not come here, so I may need here once more. So, this here, that implies f from I to j both are open is 1 1 on 2. You have a local solvability. So, if you look at here, what it says that if you take any point here for which f prime is positive, it says that there is an interval here, and then you look at its image, you look at its image, and so interval here, so you get an interval here j, this is your interval I, and here you can every point here you can solve it. Unique, you have a unique solution. So, you know the local solvability here, you see. So, if somehow the derivative, non vanishing of the derivative in one dimension, you already know that there is a solvability, and this, that is what we have observed in the previous case, in the previous example of this thing. Okay. Now, let us come back to this equation. This equation, this is nothing but the equation of the circle. You see, this is the equation of the circle here. And look at here, for this trouble you can immediately, if you look at its derivatives f x, f y, if you look at it f x, this is 2 x and this is 2 y, and then the troubling points you can immediately see that if you take 0 plus or minus 1, this is equal to 0, and if you take f y at plus or minus 1, 0, this is also equal to 0. So, these are the 4 points. Okay. So, let me mark with red color. So, you have 4 points here, and you have 4 points here, you see. Other points, if you choose any other point x naught here or anything x naught here, and if you look at its corresponding image, you have a y naught here, and you can find a neighborhood here always, and then corresponding neighborhood here, and that happens in all points here. For x naught on this part you look at it here. So, if you look at a point x naught y naught here, then with x naught, similarly if I look at a point here, you can solve it. But now look at these points. So, let me draw once again the picture. This is just for an example. Okay, so, let us look at this point. Only one point I describe, other points does not look like a circle, but that is fine. So, look at this point. This point is 0 1. Okay. So, if I look at this point, if I choose a neighborhood of point in the y axis, so I am keeping x fixed, this here value, the x naught value is 0. So, your x naught y naught value is equal to 0 1, and I want to know. So, the question is that can I solve x, can we solve x in terms of y, that is the question, in a neighborhood of y naught. Y naught is 1, you have to understand that question. So, we are looking for the solvability of x in terms of y. So, if I choose y here, I have no solution. If I choose y equal to 1, of course, you have a solution. If I choose v, I have 2 solutions, you see. So, there is a lack of unique solvability, but that is why, that is because you have at that point, this is this point. So, the derivative of f x at that point with respect to x equal to 0. So, whenever the derivative of f with respect to x, then solving x in terms of y has an issue, but then there is no issue to solve y in terms of x at that point. So, these 2 points you have a difficulty of solving x in terms of y, and there is no issue of solving y in terms of x, because that does not vanish, because this is 2 y. Similarly, these 2 points, if you look at it, you will have a problem the other way. So, I would like you to work out these kind of issues. These are very simple examples, and for these simple examples you do not have much difficult. You can understand these examples are very familiar and is directly available to you. So, look at all these points, but what we sense here is a the derivative, the vanishing of derivative creates an issue in the solvability. We need to generalize these concepts in the higher dimensions and eventually in the infinite dimension. For that you require the concept of a derivative, which is what we are going to do it now. Okay. So, let us go to the next page. So, the problem is that major issue is that what to replace f prime of a when f is from say R n to R n. Okay. So, yeah, one particular case you know in easily, you can see what it will be case when f is linear. When f is linear, essentially means f is given by a matrix A, Ax, where A is n by n matrix, and you want to know the solvability of Ax equal to 1. You know from linear algebra the complete analysis of it, right. So, one case is that if A is invertible, you see invertible, that is determinant of A not equal to 0. That immediately implies you can solve x uniquely A inverse of y, and this is the global condition. So, you can solve globally, you can solve globally. So, one condition of determinant of A not equal to 0, you need to do this one. So, you want to basically replace this n by n matrix into condition. How do you do, what kind of conditions you can replace for n f is from R n to R, which is not linear. Okay. So, we will be doing that. Okay. Now, so, I want to make a direction. First I will define what is called a directional derivative. Okay. All right. So, you already know about the partial derivatives df by dxj for 1 less than or equal to j less than or equal to a. Now, so that means for a directional partial derivative, if you want to define a derivative at a point or any point, you make changes, small changes in the coordinate axis, but I can change any direction, that is what will provide me the. So, you take a v in R n. Here I want to tell you something, you can view a point v, either you can view it as a point or you can also view it as a vector. The advantage of viewing it as a vector, you can replace this vector anywhere you like it, but the it gives you only the direction and magnitude. You can replace v. So, all same v we represent. So, not this direction. So, you have these are all v if you replace it. So, when I write a vector here, this is not a point here, it is a vector, and the point may be here as a point view. So, this is useful, you would have seen it when the motion of a particle. When the motion of a particle, you see the position you view it as a point, but the velocity you view it as a direction. That is how you represent, which we are familiar. So, given a function So, I want to define, so let me go to the next page. So, I want given a vector here V in Rn, okay. I want to define what we call it a direction. So, I want to look for the change in that direction Tv minus f of x by t, okay. So, that is what I try to do it. I call this the derivative, if x is derivative of v at the point x in the direction v, if the limit x is limit t tends to 0 x is, then you call it derivative of f, derivative of f at the point x, at the point x in direction p, okay. And if mod v equal to 1, you know that is a unit vector, then that then we call it is the directional derivative, then this is called directional derivative. So, otherwise it will have a factor directional derivative, okay. So, if this x is, you will have it. So, clearly this is called the directional derivative. Clearly if you take v equal to the unit vector Ej, where E1 etc. is the standard basis, which all of you know, standard basis of Rn, okay. Then dv Ej of f at x is also the nothing but your known partial derivative. So, you see, so you have derivatives defined in all directions. So, if you have a point x, if you have your t here, if this is your v, your Tv will x plus Tv will be here, this is the point. So, when t changes, this changes along this direction, okay. When t becomes smaller and smaller, it will be in this direction, you have to see, do not need arrow. So, it moves here. So, t becomes smaller and smaller, the values of f changing along that direction. So, I do not want to elaborate and start giving example, because I said I do not have time for all that. So, what I want to tell you here, one is this enough, is the existence of dv of x for all E v is enough for our analysis, enough for our analysis. Unfortunately, so you may think that you are taking derivatives in all directions, and one of the desirable which you know in one dimension, what is desirable? Differentiability implies continuity. This is the one minimum requirement we always look for. So, whenever you are defining a concept of differentiation, you look for its continuity. Unfortunately, the example which I am stating here, and I request all of you or suggest all of you to do this problem, okay. So, I define f of x y, this is a 2-dimensional example, is equal to x y square by x square plus y power 4. So, x y is different from 0, okay. At 0 you define 0, okay. Then you can show that. So, this is an exercise for you, show that, okay, dv of f at 0 0 X is for all V, but F is not continuous. The issue, probably those who are already familiar why this is happening, is that when you are dealing with a point, you are taking derivatives in all directions. You see, you can take derivatives in all directions, but the thing is that you can possibly approach this point not only in a linear direction, you can approach this point like this also, and that kind of approach of limiting. So, in this particular f of x plus t y minus f of x by t, you are approaching only along the straight line. You are not approaching, it is possible that you can take the limits not along the line, you can also take along various curves, and this is also the continuity, checking continuity, that f of x y, the continuity of f at the origin, you have to show that f of x y goes to f of 0 0 for all x y going to 0, not just along that one. So, you can have the variations, ratio variations along arbitrary curves, that is what. So, you have to, when you are taking a differentiation, you have to incorporate that also, that is where the difficulty of defining the differentiation. So, we will go little more, that we will do the definition, and then we will just give you the definition of the stronger definition. It is called the Fresher derivative, Fresher derivative, and this is also called Fresher derivative, or you also call it total derivative. Okay. So, you have your function f from Rn to Rn, and you fix some x naught in Rn, fix x naught in Rn, and then we say f is differentiable at x naught if there exists a linear transformation P from Rn to Rn such that if you look at the f of x naught plus h minus f of x naught minus f of x naught minus t of h modulus by modulus of h, its limit h tends to 0 is equal to 0. So, the existence of a Fresher derivative is a linear transformation. So, in this case we denote f t is equal to the derivative of f at x naught. So, it is a linear transformation, it is not a value as such. In one dimension you eventually represent it as a value, but it is a linear transformation from Rn to Rn. Okay. So, you can prove some simple exercises or study more about it. If t exists, it is unique. Okay. We have one thing, if t exists, it is unique. The second condition, you can also this replace one case. Secondly, if f is linear, suppose if f is linear, that is f of x equal to a x, then you can see that then you can easily see that f of f prime at x naught is a, you make sure that it is a linear transformation. So, it is a matrix for all x naught. that is f prime of x naught acting at y is equal to a y. So, that is the meaning of it. So, I will do a little more about it. Fresher derivative, I will one of the two results we want to present based on the Fresher derivative, put the conditions on the Fresher derivative or the existence of your derivative, and based on that we prove the solvability. We try to state two theorems, mainly the inverse function theorem and implicit function theorem. So, we will stop here and continue in the next lecture. Thank you.